ever wondered why data structures are considered a fundamental part of computer science? If you've pondered this question, you're not alone. Data structures are indeed the backbone of computing. They allow us to manage and organize data in a way that's efficient and straightforward, making our digital lives run smoothly. Imagine a library without a cataloging system. It would be almost impossible to find the book you're looking for amidst thousands of others. That's where data structures come into play. They are our digital librarians, keeping our data organized and accessible. Data structures are also crucial for problem-solving in computer science. They provide the framework for designing powerful algorithms, allowing us to tackle complex computational problems with ease. Whether it's searching for a file on your computer or finding the shortest route on a map, data structures are working behind the scenes to deliver the results. Without data structures, we would be lost in a sea of data, unable to make sense of it all. Scene script. Let's dive into the world of data structures, starting with arrays and linked lists. Arrays essentially are like the neatly organized cupboards of the data structure world. They store elements of the same type in a contiguous block of memory, with each element accessible via its index. Think of arrays as a row of lockers, where you can directly access any locker by its number. Their strength lies in their simplicity and efficiency when it comes to accessing data, as you can get to any element directly without passing through others. However, their main drawback is the fixed size, which makes them less flexible. On the other hand, linked lists are the free spirits of data structures. They store elements in separate nodes, each containing the data and a reference to the next node. Picture a scavenger hunt where each clue leads you to the next. This allows for dynamic size adjustments, making them ideal when the amount of data isn't known in advance. But it comes with a trade-off. Accessing an element in a linked list requires traversal from the start, which can be time-consuming. So when should you use which? If you need quick random access and know the data size, go for arrays. But if you need flexibility and size, linked lists are your friend. Arrays and linked lists, though simple, form the building blocks for more complex data structures. Next in line, we have stacks and queues. Picture a stack of books. The first one you put down is the last one you'll pick up. That's the principle of a stack, a data structure where the most recently added element is the first one to be removed. We call this LIFO, last in, first out. Now, imagine a queue at a bus stop. The first person to arrive is the first to board. That's a queue for you, a data structure where the first element added is the first one to be removed, known as FIFO, first in, first out. Stacks are great for things like undo functions in software or maintaining program execution in operating systems, while queues are perfect for managing tasks in a sequence like print jobs. However, they can be slower and use more memory than other data structures. Stacks and queues are the backbone of many algorithms and are thus indispensable in computer science. Now, let's venture into the fascinating world of trees and graphs. Trees, not the leafy ones but the data structure kind, are a unique type of data structure where data is stored hierarchically. Each data element or node is connected to one parent node and can have multiple child nodes. The topmost node is the root, and the nodes with no children are the leaves. Trees are used in many areas, such as file systems, where each folder is a node and subfolders are child nodes. Graphs, on the other hand, are a tad more complex. In a graph, any node can be connected to any other node, breaking the hierarchical structure seen in trees. Think of it as a social network, where each person is a node and every connection between people is an edge. Both trees and graphs have their advantages. Trees, for instance, offer efficient searching and sorting, while graphs provide a more realistic model of real-world scenarios. However, they are not without their disadvantages. Trees tend to use more memory due to the storage of additional information like pointers to child nodes. Graphs, while flexible, can be more complex to navigate and process. Trees and graphs, with their hierarchical and interconnected nature, open up a whole new realm of possibilities in data organization. It's time to wrap up what we have learned today. We embarked on a journey to understand the importance of data structures in the realm of computer science. We discovered that data structures are the building blocks of efficient coding, allowing us to organize, manage, and process data effectively. They are the backbone of many software applications, and understanding them is crucial for any budding computer scientist. Let's take a quick tour back to the structures we've demystified today. First up were arrays and linked lists. Arrays, with their static nature, offer quick access to elements but can fall short when it comes to memory utilization and insertion or deletion of elements. On the other hand, linked lists, being dynamic, provide flexibility in memory allocation and ease of insertion or deletion, though they might require more memory and time to access elements. Then we moved on to stacks and queues. Stacks, with their last-in, first-out LIFO principle, are perfect for situations where we need to reverse an order or backtrack, like in browser history or undo operations. Queues, operating on the first-in, first-out FIFO principle, are ideal for maintaining a sequence of operations or services, like in print spooling or task scheduling. Last but not least, we learned about trees and graphs. Trees, with their hierarchical structure, are great for storing data that naturally forms a hierarchy, like a file system. They also allow quick search, insertion, and deletion operations. Graphs, due to their ability to represent complex networks and relationships, find wide applications in social networks, web pages, routing algorithms, and more. Each of these structures, with their unique characteristics, uses, advantages, and disadvantages, play a vital role in the world of computing. Understanding them and knowing when to use which one can significantly optimize our code and tackle complex problems with ease. Remember, mastering data structures is a significant step towards becoming a proficient computer scientist. So keep exploring, keep learning,